Welcome to the deep dive, everyone. We love getting right to the good stuff, the fascinating ideas, and today I think we've got a really great one. You know how we always talk about the best way to learn something? Well, get this. The best way to learn something actually changes depending on how much you already know about it.
Yeah, it's really not one size fits all.
Not at all, right?
No. And today we're diving into this really fascinating paper. It's called The Expertise Reversal Effect is a variant of the more general element interactivity effect.
Catchy title.
Yeah, right. It's from Educational Psychology Review. And it's going to help us really understand this whole idea.
I'm excited to dig in because I'm already kind of mind blown. Like why does a learning method that's perfect when you're just starting out, you know nothing, why does that same method become like totally useless or even bad for you once you gain experience?
Right. It's like, why do those training wheels suddenly start holding you back?
Yeah, exactly. That's the mystery we're going to try to solve today.
Absolutely.
Right.
And this whole thing, it's called the expertise reversal effect. It basically means that a teaching method or a learning strategy that really helps beginners, like boost their scores on tests and stuff, it can actually make it harder for those same learners to progress once they know more.
So it's not just about finding like the best way to learn anything, period. It's about finding the best way to learn for you at this moment, right? Like where you are on your learning journey.
Right. Yeah. Like how much do you already know?
Yeah.
That makes a big difference. And the paper that talks about two types of this effect, right? There's this thing called an ordinal interaction.
Okay, ordinal interaction.
Yeah. And this is where a method, it's really effective for novices, but then it kind of, as people become experts, it sort of loses its power or it just has no effect anymore. Like think of it as like a gentle slope downwards in terms of how effective it is.
Helpful at the start, but then it's just, eh.
Right, exactly.
But then there's the other one, right?
Yeah.
The more dramatic one.
Yeah, right. That's called a disordinal interaction. And this is the one where a learning method that is super helpful for beginners actually becomes like straight up bad for experts.
Whoa, so completely flips.
Yeah, it's a complete 180. What helps one group actually hurts the other.
Wow, so the thing that helps you get started can actually hinder an expert. That's wild.
Yeah, and the paper mentions that the bigger the difference in knowledge between learners, the more likely we are to see this really dramatic flip.
The bigger the gap, the bigger the flip. Okay.
It makes sense, right? Like think about learning to ride a bike.
Yeah.
If you're a total beginner, training wheels are like essential.
Yeah.
But if you've been riding for years and you try to use training wheels,
You're going to fall.
yeah, you're going to fall, or at least it's going to be a lot harder, right?
Right. So that really makes sense.
Right, like you got to switch gears as you get better. You got to switch gears. So the paper actually dives into a whole bunch of real-life studies where they saw this effect happening, like in different subjects in different fields. Can you give us some examples of that? Yeah, tons of them. So one of the early ones was about engineering apprentices. They were learning, stuff about engineering. And the researchers found that when they gave these apprentices text explanations right there with the diagrams, integrated together, that was much better for the novices. Like they really needed that text to understand what they were looking at.
It makes sense.
Right. Like they didn't have the background to just look at a diagram and understand. But as these apprentices got more training, more expertise, the diagrams on their own, like without all the text, became more effective.
Ah, so the text actually started to get in the way.
Yeah, it started to feel redundant. It was like, yeah, I get it already.
Like, I don't need you to over-explain it to me.
Right, exactly.
Yeah.
It actually became a hindrance because it was just cluttering things up.
So the thing that helps you at the beginning can actually become a distraction later on.
Yeah, that's exactly what they found.
I see. What about in other fields? Did they see the same pattern?
Oh, yeah, all over the place. Like there was this other study, it was with mechanical engineering students, and they were learning how to understand diagrams, these like kind of complex diagrams. And they found that at first, when the diagrams had like narrated explanations and they were animated, that was really helpful for the beginners. But once the students had learned more, they understood the basics, those narrations actually became a problem.
Oh, interesting. So it was like they didn't need that hand-holding anymore.
Exactly. It's like once you've built that foundation, you don't need someone to hold your hand through every step anymore. The more knowledgeable students actually learn better when it was just the diagrams, like, let me figure this out on my own.
So it's not just about getting distracted. It's almost like they have a more efficient way of processing the information now.
Yeah, that seems to be part of it. Like
Yeah.
the extra guidance was messing with their process. They had developed a better way of doing it.
Wow, so it's like their brains upgraded and the old methods don't work as well anymore.
Yeah, kind of, yeah. And another cool example is, let me think. Oh, yeah, this study on relay circuits. They found that initially, like at the start, it was better to show students worked out examples, like here's how this circuit works step by step. That was more effective than having them try to, figure out the equations on their own, like in writing. But then guess what? After more training, that totally flipped.
The students who had more practice, they preferred to grapple with the equations.
Exactly. The ones who knew more, they learned better by actually engaging with those equations, like struggling with them a bit. The challenge became beneficial.
It's like they were ready to take off the training wheels.
Exactly.
So it's like as you become an expert, you actually crave that challenge more.
It seems that way. Like, it's not just about passively absorbing information anymore. It's about actively using your knowledge, grappling with it.
I see. And this whole thing, did it hold true for other types of math too?
Oh, yeah, definitely. Like, there were studies on coordinate geometry where they saw the same thing. Learners who didn't know much about it beforehand, they learned better from worked examples. But the ones who already had a good grasp of the concepts, they did better by, jumping into problems and figuring them out themselves.
Interesting.
Yeah. And in algebra, they found that students who had already practiced a lot, they actually did better with less step-by-step instruction. Like, give me the problem, let me figure it out. But the novices, they definitely needed those clearer instructions.
They needed the scaffolding, like the support structure.
Exactly.
It's so cool how consistent this is across like different areas of math, It's like a fundamental principle of learning.
Yeah, exactly.
And it's not just math, right? It's not just technical stuff. The paper talks about statistics too.
Right. In statistics, they found that students who were new to it, they learned more from, good old worked examples. But students who already knew a decent amount about statistics, they did better when they had to answer open-ended questions and, like, actually explain their reasoning.
Ah, so they had to really think it through and justify their answers.
Yeah. The experts needed to actually apply their knowledge, not just, like, passively absorb it.
They had to go deeper. And what about like learning a complex algorithm? Did they study that too?
Oh, yeah. They looked at things like gradient descent, which is used in machine learning. And they found that students who already had more experience with it, they performed better when they learned from, like, an animation without any extra text explanations. But the beginners, they definitely needed that text to guide them.
It's like once you understand the concept, you don't need all the extra fluff.
Right. Once you have the foundation, the extra stuff can actually get in the way.
This is this is really amazing. It seems like this principle is so widespread, like it's true across so many different areas. Even in English literature, they found this, right?
Yeah. They looked at how people learned Shakespeare, and they found that students who weren't familiar with his work, they did better when they had modern English explanations integrated into the original text, like translating it as you go.
Right, helping you understand what you're reading.
Yeah. But for people who are already, you know, Shakespeare experts, those explanations were just annoying. They preferred just footnotes.
It's like they wanted to appreciate the original, like without someone dumbing it down for them.
Exactly. They already had the context. They didn't need all that extra help.
So cool. And this applies to writing too, right? Like learning how to write.
Yeah. There was a study on journal writing, and they found that giving prompts was really helpful for novice writers at first. Like it gave them something to work with, some structure.
Yeah.
But as they got more practice, the benefit of those prompts actually reversed.
So like as they became more comfortable with writing, they didn't need those prompts anymore.
Right. They were able to come up with their own ideas, and maybe the prompts were even a little stifling.
I see. So even in creative fields, you need that initial support. But eventually you want to break free and do your own thing.
Yeah, exactly. It's about finding that balance between support and freedom.
So we've seen this effect in engineering, math, statistics, English literature, writing, and the paper even mentioned something about troubleshooting problems, right?
Yes, in troubleshooting tasks, the type of worked examples they gave learners made a difference. Process-oriented examples, the kind that walk you through why each step in solving the problem is necessary, those were more helpful for novices. But for experts, it was the product-oriented examples, the ones that just show you what to do, the steps. Without all the explanation, those were better.
It's like the experts are saying, just show me what to do. I don't need the lecture on why.
Exactly. They already understand the why.
Amazing. And it even applies to how we learn with technology, with computers and stuff.
Oh, yeah, absolutely. In computer-based learning, they found that novices benefited from having, like, extra text explanations within the program, but more expert students did better without them. And then with multimedia learning, you know, videos and stuff, students with a lot of prior knowledge often did better without an animated character, like, a little guide telling them what to do.
Hmm.
But for learners who didn't know much, that guide was actually helpful.
So again, it's like once you get it, you don't want someone holding your hand.
Right.
This is all like really clear now, right? Across all these different subjects, areas of knowledge, beginners, they need more guidance, more information. But as you become more expert, that same support can actually become a problem. It can hinder your learning.
Yeah, that's the big takeaway.
But the paper goes on to say that these early studies didn't actually connect this expertise reversal effect to another important concept, this idea of element interactivity.
Right.
So what is element interactivity exactly?
So element interactivity is a key concept in something called cognitive load theory. It basically refers to how many pieces of information you have to process in your working memory all at the same time.
Okay, at the same time? Why all at the same time?
Because they're related, right?
Yeah.
Like they depend on each other.
Yeah.
You can't understand one without the other. An element could be like a symbol, a concept, or, a step in a procedure.
So it's about how interconnected, how complex the information is.
Exactly. It's like how many things do you need to be thinking about at once to make sense of this?
Hmm.
And the level of element interactivity in a topic, it tells us a lot about how difficult it is to actually understand, especially if we're trying to learn it for the long term.
I see.
And the number of interacting elements, it's not like a fixed thing. It changes depending on the material itself and also how much the learner already knows.
Okay, so for someone who's totally new to like a really complex topic, there might be a ton of elements that feel connected and they're trying to juggle them all in their mind.
Exactly. And this is related to what we call intrinsic cognitive load.
Intrinsic cognitive load. Okay, another term.
Yeah, but it makes sense.
Yep.
Intrinsic cognitive load is just like the inherent difficulty of the material itself. So if something has high element interactivity, like, trying to understand a system with a lot of moving parts, that's going to have a high intrinsic load. It's
Well,
just naturally more difficult to process all those things at once.
right, your brain is working harder.
Exactly. But then if something has low element interactivity, like let's say just memorizing a list of vocabulary words, that's going to have lower intrinsic load because you can process each word kind of separately.
So intrinsic load is about the complexity of the material, and element interactivity is how we measure that complexity.
Yeah, that's a good way to think about it.
Okay, so now we've got these two concepts. Intrinsic load, element interactivity. Where does expertise fit in?
Well, here's the interesting part. A learner's expertise actually reduces intrinsic cognitive load.
Wait, really? So the more you know, the easier it gets?
Yeah, because as you gain experience, as you start to develop like mental models of how things work, all those individual elements that used to seem separate, they start to come together. You start to see them as chunks, as like these integrated units.
Ah, so instead of seeing a bunch of separate trees, you start to see the forest.
Exactly. And these chunks, we call them schemas. So you're not processing each little piece individually anymore. You're processing these bigger, more meaningful units.
It's like learning to read. At first, you're sounding out each letter. But then you start recognizing whole words, then phrases.
Right. That's a great analogy.
Okay, so expertise makes it easier because you're not dealing with as many individual elements anymore.
Exactly. But the paper also points out something really important. Element interactivity isn't the same as task difficulty.
Wait, what? So something can be difficult but have a low element interactivity.
Yeah. Think about it. A task could have a lot of elements, like a lot of things to learn, which makes it seem difficult, but those elements might not be that interconnected. Like, let's say you're learning a bunch of vocabulary words in a new language. That's a lot of stuff to remember, right? But each word meaning pair, it's kind of separate. You don't need to understand one to understand the other.
So it might feel difficult because there's a lot to memorize, but the element interactivity is actually pretty low.
Exactly.
Okay, that makes sense. Now, how does this whole idea of element interactivity relate to actually understanding something? Like, what does it mean to understand something from this perspective?
So understanding usually means that you can process all those key interactive elements together at the same time in your working memory. But we usually only use the word understanding when we're talking about material that have high element interactivity.
What do you mean?
Well, if something has low interactivity, like remembering a date or a fact, we don't usually talk about understanding. It's more like you just remember it. But when you understand how something works, like you understand a system, a concept, that usually involves high element interactivity. You're putting all these pieces together in your mind.
I see. So I understand how an engine works, but I just remember that the Battle of Hastings was in 1066.
Exactly. One involves a lot of interconnected elements, the other is just a fact.
Okay. Now, we've talked about intrinsic load, element interactivity, expertise. What about extraneous cognitive load?
Right. So extraneous cognitive load is all the mental effort that comes from bad instruction. It's like the teacher's making things harder than they need to be.
So it's not the inherent difficulty of the material, it's the extra difficulty added by the way it's taught.
Exactly. And element interactivity is important here because bad instruction can actually increase extraneous load, especially if it forces experts to process information in a way that's less efficient than how they would normally do it.
It's like forcing that experienced reader to sound out each letter again, instead of just reading the words, right?
Right, like you already know how to do this, why are you making me do it the hard way?
Hmm.
And this brings us to something called the element interactivity effect.
Okay, another effect. The element interactivity effect.
Yeah, it basically says that those other cognitive load effects we've talked about, like the worked example effect, they usually only happen when the learning material is complex, when it has high element interactivity. If the material is already simple, if it has low intrinsic load, then even if the instruction isn't great, it might not matter as much.
Because the total load on your working memory is still manageable.
Exactly.
Okay, I think I'm starting to see how all these pieces fit together. But how do the expertise reversal effect and the element interactivity effect relate to each other?
Okay, so this is like the big idea of the paper, the main argument. They're saying that the expertise reversal effect isn't a totally separate thing. It's actually a specific type of the element interactivity effect.
So there's like a subcategory.
Yeah, exactly. They're arguing that both of these effects are basically about changes in how much element interactivity there is, but the difference is what's causing that change.
Okay, I'm listening.
So in the element interactivity effect, the amount of interactivity, it's determined by the material itself,
Hmm.
right? Like, how complex is this topic inherently?
Yeah.
But in the expertise reversal effect, the change in interactivity is because the learner is getting more expert.
Hmm.
They're understanding things better, so it feels less interactive to them, even though the material itself hasn't changed.
So it's not the material that's changing, it's your perception of the material that's changing as you become more expert.
Exactly.
Okay. So as you gain expertise, something that felt really complex and interconnected at first, with all these elements, it starts to feel simpler, less interactive because you've built the mental frameworks to handle it.
Exactly.
Wow. So high expertise reduces element interactivity and low expertise increases it, even for the same material.
That's it.
This is so insightful. Now, the paper also talks about how this all relates to the architecture of our brains, like the basic principles of how our minds work.
Right. They talk about these things called the human cognitive architecture principles, which are like basic rules of how we learn and process information.
Okay, can you break those down for us?
Sure. There's the borrowing and reorganizing principle, which says that most of what we learn from other people at first. We're not just figuring everything out from scratch.
Yeah.
Then there's the randomness as genesis principle, which is kind of funny. It says that new knowledge, like brand new ideas, they often come about through trial and error.
We're just messing around, trying things out, and boom, we discover something new.
Yeah, kind of. And then there's the narrow limits of change principle, which is about how our working memory, the part of our brain where we process new information, it has really strict limits.
It gets overloaded easily.
Yeah, it can only handle so much new stuff at once.
I can relate to that.
Right. And then there's the information store principle, which is basically about long-term memory, the part of our brain where we store all our knowledge. And that part, thankfully, has pretty much unlimited capacity.
It's like a giant warehouse.
Yeah, exactly. And lastly, there's the environmental organizing and linking principle, which explains how things in our environment can trigger memories, activate knowledge that we stored away. And when that happens, tons of information can flow from long-term memory back into working memory, where we can use it.
So it's like our environment is giving us cues that unlock relevant knowledge in our brains.
Exactly.
Okay, so how do all these principles, how do they relate to this whole element interactivity and expertise thing?
Okay, so think about it like this. When you're a novice, you don't have a lot of those knowledge structures, those schemas, stored in your long-term memory yet, right?
Okay.
So when you encounter new information, it feels like a whole bunch of separate interacting elements, and it's overwhelming. Your working memory is like, whoa, too much.
It's like trying to drink from a fire hose.
Yeah, exactly. It's too much information at once. So it feels like high element interactivity, and the intrinsic load is high. And because you don't have those schemas yet, you might also rely more on random guessing and trial and error, which just adds more cognitive load.
It's like you're just flailing around trying to make sense of it all.
Yeah, that's a good way to put it. But now think about an expert, someone who knows a lot about this topic already. They do have those schemas, right? Those well-developed, interconnected knowledge structures stored in their long-term memory. So when they encounter that same information, they can use their existing knowledge to make sense of it. They can chunk those individual elements together into bigger, more meaningful units. So the element interactivity feels lower, and the intrinsic load is lower.
It's like they have this mental map that helps them navigate the information.
Exactly. And they can also retrieve relevant knowledge from their long-term memory really quickly and efficiently, so it doesn't overload their working memory.
So expertise is like having a superpower.
In a way, yeah. It lets you handle much more complex information without getting overwhelmed.
I like it. Now, the paper goes on to use the worked example effect as like a specific illustration of all this. Can you walk us through that?
Sure. So remember, the worked example effect is this idea that for novices, it's often better to study fully worked out solutions to problems than to try to solve the problems themselves.
Right, because it gives them a model to follow.
Exactly. And from this element interactivity perspective, it makes sense. When a novice sees a problem, they've got all these things swirling around in their head, the problem statement, the possible steps, how those steps relate to the answer they're trying to get to. That's a lot of element interactivity. But when they study a worked example, it kind of reduces that interactivity because it gives them a clear, correct path to follow.
So the worked example makes the problem feel simpler.
Right. It reduces the cognitive load. But now, imagine an expert looking at that same problem. They probably already have a pretty good idea of how to solve it, right?
They have that schema stored in their long-term memory.
Exactly. So for them, studying a worked example might actually be unhelpful. It's like, they already know this, why are you showing me this? It's redundant, it's extra information that they don't need, and it can actually increase element interactivity because now they're comparing their own knowledge to what's in the worked example.
So it's making them think more than they need to.
Exactly. It's adding cognitive load. For an expert, it's probably better to just solve the problem on their own using their existing knowledge.
So for experts, problem solving is the lower element interactivity option, and worked examples are higher.
Yeah, that's the idea. And this reversal is why worked examples help beginners, but might actually hinder experts.
Because of this whole element interactivity thing.
Exactly.
Okay, that makes a lot of sense. Now, did they find any research, like any studies that actually support this idea, this link between the two effects?
Oh, yeah, there are a few.
Yeah.
Like, there's this study by Kalyuga and some others in 2001. It's the one we talked about before with the worked examples. And they found that the worked example effect, where worked examples are more helpful for novices, it actually disappeared when the learning material had low element interactivity.
So when the material was already simple, the worked examples didn't really make a difference.
Yeah, exactly. And then, get this, the effect actually reversed when learners had more expertise. So worked examples actually became worse for the experts than just solving the problems on their own.
Wow, so the way you learn best isn't just about you, it's about you and the material.
Exactly. It's about both.
That's fascinating. Were there any other studies that looked at this?
Yeah, there's this other one by Lickey and Sweller in 2005. They were looking at this thing called the imagination effect, where more knowledgeable students sometimes learn better by imagining how to do something rather than just like reading about it. And they found that this effect only happened when the material was complex, when it had high element interactivity. Less knowledgeable students, they didn't show the imagination effect. They needed to actually study the material.
So for simpler stuff, it didn't matter if you imagined it or studied it, but for complex stuff, imagination was better, but only for the more knowledgeable learners.
Right. And then there's another study by Blaney and others in 2010. They were looking at this thing called the isolated elements effect. This idea is basically that when you're dealing with really complex information, it might be helpful to learn the individual pieces first in isolation and then put them all together later.
Break it down before building it up.
Right. And they found this effect for less knowledgeable learners, but more knowledgeable learners actually did better when they saw the interactive elements right away without breaking them down first.
Ah, so the experts already have that mental model and breaking it down just messes things up.
Exactly.
It's like trying to explain a joke, it just doesn't work as well when you dissect it.
Right, you lose the magic.
Exactly. And was there another study that really brought all these ideas together?
Yeah, there's a really interesting one by Chen and colleagues in 2015. They looked at both the worked example effect and the generation effect.
The generation
Yeah,
effect.
that's the idea that you learn better when you have to generate the answer yourself instead of just being given it. So they looked at these two effects, and they looked at them with different levels of element interactivity and expertise in geometry.
Okay, so they were really testing this idea in a specific context.
Right, and they found that for novices, worked examples were better for problems that were more complex, that had high element interactivity. But for simpler stuff, the generation effect was better. So even with novices, the best method depended on the complexity of the material.
Wow, so the same learner could benefit from different methods depending on what they were learning.
Exactly. And then, when they looked at more knowledgeable learners, they found the generation effect, or a reversed worked example effect, for both the simple and complex material. So for those learners, it was almost always better to generate the answer themselves. And that suggests that for them, pretty much everything felt like it had lower element interactivity.
Because of their expertise.
Right. And then, when they compared novices and experts directly on the complex problems, they found the classic expertise reversal effect. Worked examples were better for novices, problem solving was better for experts.
That's so cool. It really ties everything together.
It does. It's like all these studies, they're pointing to the same conclusion. The expertise reversal effect isn't some random thing. It's a direct consequence of how our expertise changes the way we experience the information we're trying to learn.
So, to sum it all up, what we're learning here is that the best way to learn isn't fixed. It changes as you gain knowledge and skills. What works when you're a beginner might not work, or might even be harmful when you're more advanced.
Exactly. And that's why it's so important to be aware of this. Teachers need to understand it, and learners need to understand it too.
So, the key takeaway for you, the listener, is this. When you're approaching something new, take a moment to think about your current level of expertise. Are you a total newbie? If so, you might benefit from more structure, more guidance, more worked examples. Or are you more experienced? If so, you might learn better by jumping right into problem solving, by figuring things out on your own.
And remember, your level of expertise isn't fixed, it's always changing. So as you learn and grow, you'll probably find that the best way for you to learn will also change.
This has been a really fascinating deep dive. I feel like I have a whole new understanding of how learning works. And with that, we'll leave you with this final thought to ponder. How might this concept, this expertise reversal effect, change the way you approach learning in the future? How might it change the way you teach or mentor others? Thanks for joining us on the deep dive.